Hi folks, welcome to this lesson on revisiting derivatives. So we've already covered all the rules for exponentials, for trig, for logarithmic stuff. I just thought it was worth taking a look back at some of that stuff and making sure that we can do it in the context of maybe more involved functions. So we're going to find some derivatives here. We've got an exponential in this one, but we have a chain rule happening. It's not just e to the x, it's e to the, what we might call a glob of something. So the derivative, which we can write in either Leibniz or Lagrange notation, doesn't matter. E to the 6x, it's going to stay the same, times the derivative of 6x, which would be 6. For cosine, we're thinking about that wheel of trig. Sine differentiates to cosine, which differentiates to negative sine, which differentiates to negative cosine. If you go clockwise, you have your derivatives. If you go counterclockwise, you have your antiderivatives. So the derivative of cosine is negative sine. So we're going to have negative sine of, and again, we have this kind of glob situation. So negative sine of, that glob does not change. And then times the derivative of that glob. The derivative of 3x minus 5 would be 3. And so we get a final derivative here of 12e to the 6x minus 3 sine of 3x minus 5. Notice that 3 does not multiply into the angle of 3x minus 5. It multiplies in front as sort of something that would impact the amplitude. That brings us to our next one, which is sine x by ln x. And the thing that often gets missed here is the product rule. So what I'd encourage you to look for is the fact that there are two x's that do not have a plus or a minus anywhere between them. Or there are brackets involving x that doesn't have a plus or minus between them. So in this case, we have a product. It's uv goes to, you can memorize this any way you want. Maybe you have a different mnemonic device. But your u is going to be this sine x, or your first part. Your v is ln x. U prime would be the derivative of sine x, which is cos x. Maybe I'll be a little clearer here. U is sine x, v is ln x. V prime, the derivative of ln x, is 1 over x. Or you can sing it out as original on the bottom, derivative on the top. Now we can simply plug into this handy little formula. So u prime by v, which is ln x, plus u, which is sine x, by v prime, which is 1 over x. Now the first part of that, there's not a whole lot you can do with. In fact, it's probably safer to leave them with their brackets. The second part, if you wanted to, you could call it sine x over x. And let's be clear here. Those x's do not divide out. It's the sine of x divided by x. If you divided out the x's, it would literally be a sin. Moving on, we want to find the derivative of sine of ln x. So we just did one that was sine x by ln x. And so here we might be thinking, oh, this is another product rule. But it can't be a product rule because it only involves one x. This is the sine of something. This is a chain rule situation. So if we want to find the derivative, it's the derivative of sine is cosine. So we'd have cosine of that same glob that we had before, of ln x, multiplied by the derivative of ln x, so the derivative of that glob, which is 1 over x. In prettier form, that would be dy by dx is cos of ln x all over x. Now, this function only exists where x is greater than 0. That's implied because we have a ln x involved. You can only take the log of positive numbers in the real number system. And now we've got to find the lowest x value that produces a horizontal tangent. So we're trying to put together a bunch of different ideas in this video. Horizontal tangent means slope, or gradient, is 0. And dy by dx, or y prime, those are things that mean slope. So let's put in 0 for slope. We'd get the cos of ln x over x equals 0. And I could multiply both sides by x to try and solve this. because I don't really like those fractions. Oh, I'm still going to get 0 equals cos of ln x. That's a trig equation, and it's a weird one. And it's asking for the first place that this happens. Well, let's see. Where's the first place that cosine is 0? I'm going to draw myself a little unit circle here. Right here is where we have the first place where cosine's 0. We have another place that cosine's 0 over here. But at the first angle, that would be the angle of pi over 2. So we can solve this. And at any point you want to pause and just try this stuff, probably so much the better. So pi over 2 is the angle that we get. And normally, if it had been cos x equals 0, we'd say, the first answer is x equals pi over 2. But here it's not x that we have. The angle that we have is ln x. So we're going to have to say ln x equals pi over 2. And then to break out of our logarithmic form, we're going to need to convert to exponential form. So because we have a natural logarithm, that means a base of e. The power is pi over 2. And the result is x. If you wanted to, then you could write that as the square root of e to the pi equals x. Lots of fancy numbers here. Okay, you could write it this way, or you could write it this way. Both are correct. So to recap, this question had a lot in it. We had a chain rule. We had to differentiate using that. We had to infer that a horizontal tangent means a slope of 0. We had to solve a trig equation. And that trig equation had some composition. It wasn't just cos of x. So at every step, we just tried to do the next reasonable thing. We didn't worry about trying to get to the very end. We tried to do one step at a time. Let's do one more question that's going to involve exponentials and hunting for maxes and mins and points of inflection. Remember that on a smooth max or min, you're looking for a slope of 0. On a point of inflection, you're looking for a second derivative of 0. So here's the graph. It has an absolute min at A. Okay, we can see that. A local max at B. It has points of inflection at C and D. And we're asked to show that f prime is x by 2 minus x over e to the x. In a show that question, what it's asking you to do is just find f prime period, and it's being nice enough to tell you what the answer is. So if you can't do it, then you can still use the answer later on. So for a quotient, we get u prime v minus uv prime all over v squared. And right here we have a top that's x squared, so that's u is x squared, u prime is 2x. V is a gift. V is e to the x. Its derivative is also e to the x. So now we can plug and chug in the quotient rule. F prime of x is u prime, which was 2x, by v minus u by v prime all over v squared. Now I can multiply this out. So I'll get 2x e to the x minus x squared e to the x. It probably would have been slicker to just factor it out. Yes, I could turn the bottom into e to the 2x, but I know that eventually I want just e to the x on the bottom, so I'm going to leave it as is. The next thing I'll do is factor, which I might have noticed I could do earlier. And this is promising because it leaves me with 2 minus x in the brackets, all over e to the x squared. And this is the moment where we can do some true cancellation. You don't divide out terms, you divide out factors. So after we've factored, it's fair for us to simply divide out and get x by 2 minus x all over e to the x. So that's great. We've found the first derivative. Now we're asked to find the coordinates of b. So at a max or a min, we've got horizontal tangents. That means the slope is 0. So f prime is going to be equal to 0, or 0 equals that first derivative. So notice in the setup of this question, even if you couldn't do part A, you could use its result to solve here. We can multiply both sides by e to the x, and we'll still have 0, on the left. And the answers to this are x equals 0. And I guess you could do this as a little equation, 2 minus x equals 0, or x equals 2. You're asking what number zeroes out this bracket. Now, clearly A is this one over here. B needs to be this one over here. So B has coordinates. Oh my, we need to find the coordinates. Coordinates of 2 something. How are we going to find that y value? We're going to sub in to the original. So 2 and f at 2. That would be 2 squared all over e to the power of 2, or 4 over e squared. That's the coordinates of this point. Okay, let's keep going. It tells us that the second derivative is x squared minus 4x plus 2 all over e to the x. And then it says an important word. It says, hence, confirm that b is a max. So normally there'd be 2 ways that you could confirm that b is a max. You could make a sign diagram for the first derivative, and that would be great because you already have the first derivative. But since it's saying hence, it's saying you have to use this. You have to use what they just gave you. If it says hence or otherwise, you can take your pick. You can either use the second derivative or the first derivative. So the second derivative test for a max is you find this critical value, or this place where slope is 0 on the first derivative, and then you plug into the second derivative. So f double prime at 2 is going to be 2 squared, just looking at the definition there, 2 squared minus 4 times 2 plus 2 all over e to the power of 2. And let's just work that out. That would be 4 minus 8 plus 2, so negative 2 over e squared. Okay. At x equals 2, f double prime is negative, which means that we're concave down. Let's draw that. Concave down and horizontal at this point. Therefore, it must be a max. Lastly, we're asked to find the x-coordinate of c. So this point right here. That's a point of inflection. So the second derivative does a couple of things. The second derivative helps us find max and min by just testing the concavity at that point. But if we want to find points of inflection, those are places where the second derivative is 0. So we can say at c, f double prime is 0, where 0 equals x squared minus 4x plus 2 all over e to the x. Okay, because that was the definition of f double prime. They gave it to us. So you can see here, even if you couldn't do anything even up to question D, you can probably do question D, even without the stuff from ABC. We're going to multiply both sides by e to the x. You don't necessarily need to show that, but that gives us this setup right here. And we can try and factor it, because that would be most convenient. And after trying for maybe 15 seconds, we're unsuccessful. So we go to the quadratic formula. And it's negative b plus or minus the square root of b squared minus 4ac all over 2a. I plug in, I don't want to see negative, so I'm just going to put in 4 for negative b. b squared is going to be negative 4 squared, so that's 16, minus 4 times a times c all over 2a. So that's over 2 times 1. And maybe I'll fix this up. This is not a good final answer because c is only one of those x values. Now, I'm going to take the time and make this look nice. So it's 4 over 2 plus or minus root 8 over 2. Or 2 plus or minus 8 would be root 4 times root 2 over 2. Or better yet, 2 root 2 over 2. What we're learning here is that the coordinates of c and d are 2 plus or minus root 2 respectively. C is going to be the lower of those two. So C is at x equals 2 minus root 2. Okay? And it doesn't ask us for the y-coordinate here. We don't have to prove that these are points of inflection because they told us they were points of inflection. There's some practice work that's just on sort of varied stuff on page 551. I hope this has been helpful. Good luck with the material, folks, and take care.